I'm going over chemical reactions. Some of them are just a generic type of reaction, and then we're going over some specific kinds of chemical reactions. So I have listed here three different types of chemical reactions, and it's just a generic. Whenever you have a decomposition reaction, what you have is a substance that is being decomposed into simpler substances or more than one substance. So for example, here I have hydrogen peroxide, H2O2, and that one is being decomposed into water and oxygen. So you're going from one to two different things here as products. So whenever that happens, you will have a decomposition reaction. Then the second one, it's a combination reaction, which is the opposite. Okay? In a combination or synthesis, in those type of reactions, what you have, it's two or more reactants combining to give you just one product. So whenever you have something like this, you have two reactants here, and then you're getting only one product. That will be a synthesis or combination reaction. Then the third one down here, it's single displacement reaction. So you have one element that is replacing another element in a compound. So let me show you the example, and that will help you to see what's happening here. We have the element aluminum, we have the compound iron oxide, and then here in your products you have aluminum oxide and iron, the element. So aluminum is displacing this iron from the iron oxide compound, right? And now you will get aluminum oxide. And since aluminum is displacing the iron from your compound, now you have iron, the element, by itself. And I have another example here. This is magnesium and water, and that's in the presence of heat. Okay, so it's not just magnesium and water. We need to heat up that reaction. So I'm writing water down here in a different configuration. Instead of having just the formula H2O, I'm writing H and OH, the proton and then the hydroxide, the positive part on your water molecule and the negative part on your water molecule. So on your product side, you have magnesium hydroxide and hydrogen. So the magnesium is displacing the hydrogen from your water molecule to give you magnesium hydroxide. And then the hydrogen, if two hydrogens form a bond between them, you will get hydrogen gas. So whenever you have an element that is replacing an element in a compound, just one element replacing another element in a compound, that will be a single displacement. And the last general classification of chemical reactions will be double displacement reactions. When you have a double displacement, everything will be exchanged. So if you have two ionic compounds, your positive ion from one compound will combine with the negative ion on a different compound. And then the two ions that are left over, they will combine between them if they have opposite charges to give you a second product. So a specific type of a double displacement reaction, it's a precipitation reaction. A precipitation reaction, it's a type of reaction where you have a solid as a product. That solid, it's an insoluble compound. It's not soluble in water. That's why it's a solid. And the solid that you're getting, or the compound that it's insoluble in water, is known as a precipitate. It will precipitate out of your solution because it's not soluble in your solvent water. So besides knowing the definitions for your precipitation reactions, you need to know how to predict the products of a reaction and how to identify which one out of your two possible products, which one is going to be the actual insoluble compound. So I have here two compounds, barium chloride and sodium sulfate. Now, what you're doing here to predict the products of your reaction is just writing the formula for an ionic compound. The same thing that we did in nomenclature and formula writing, exactly the same thing. You're combining positive and negative ions. Now, when you have a compound, your compounds, they are neutral. They don't have an overall charge because your positive charges and your negative charges, they need to cancel out. So you need to have the same number of positive and negative charges combined in a formula to get your neutral ionic compound. So we're doing exactly the same thing. We're writing formulas for your two possible products for this specific reaction here. So when you have your formulas for your ionic compounds, the first element in your formula is the positive or the metal. And then the second one will be your non-metal or the negative ion. It can be a polyatomic ion like in this example here. So positive always first and then the negative one. So in your barium chloride, the formula is BaCl2 because barium is +2, group 2 +2. Cl, it's chloride, the ion of chloride. Chloride is in group 7, charge of -1. So if barium is +2, you need two chlorides to cancel out your two positive charges. Sodium sulfate, right there, the formula is Na2SO4. Sulfate, your polyatomic ion sulfate, is SO4 -2. And sodium is Na+1 because sodium is in group 1. So if you want to cancel out the two negative charges from your sulfate ion, you need two positive or two sodium ions. That's why the formula is Na2 to cancel out your two negative charges for that one. Now those are your two reactants. And I already told you, I'm giving you that they are aqueous because both of them are soluble in water. But you can check that with your solubility rules. Barium chloride, chlorides are soluble, is your rule number 3. Chlorides are soluble. You have some exceptions in there, but barium is not one of your exceptions. So barium chloride is soluble. And then sodium sulfate, that's your rule number 1. Any compound containing elements from group 1, they're always soluble. So sodium sulfate is soluble. Now, to write down your two products, the first thing that you're going to do is combining your ions with opposite charges. Just the ions, okay? You're going to ignore any subscripts. You're just going to combine the ions and then we will find out if we need a subscript or not. When you're working with polyatomic ions, you're going to look at your polyatomic ion as a whole unit. All of that is your sulfate ion. Polyatomic ions are a whole unit because what you have holding together your polyatomic ion are covalent bonds. S, non-metal, O, non-metal. So all of them are held together by covalent bonds and you have an overall charge. That's why you can have ionic compounds with polyatomic ions, because your polyatomic ion will have an overall charge, and then that one can combine with opposite charges. So your polyatomic ion sulfate is a whole thing, a unit, negative, and look at the arrows with positive. And then I have my negative here, which is the chloride, with the positive on the other one. I'm going to write down just the ions, no charge, just the symbol for the ion. Ba, go with sulfate. And then I have Na, and that one goes with the Cl. You see how I'm not transferring Cl2. I didn't transfer the 2, I'm transferring just the symbol for your ion chloride. I'm not transferring the 2 for Na. No, I'm just transferring the symbol. Positive with the negative, and then the positive with the negative. So I have 2 new combinations. Now you have to check the charges of your ions. Look, barium, it's in group 2. The charge is +2. Polyatomic ion sulfate, the charge is -2. Sodium, it's in group 1, that's +1. And Cl, it's in group 7, that's -1. Same positive and negative charges. You don't need any subscript because your charges are going to cancel out. +1, -1, you don't need any subscript. So when you combine the barium with the sulfate, no subscript is required because you have the same charge with opposite sign. When you combine Na with Cl, you don't need any subscript because this one is +1 and that one is -1. So to write down the products of your precipitation reaction, you're exchanging the ions. A double displacement is happening because the barium, it's replacing the sodium here because you're combining the barium with the sulfate, and then the sodium is being combined with the chloride. You're going to combine the ions, ignoring any subscripts that you have, besides the subscripts that are part of your polyatomic ion, SO4. It's a whole thing, SO4, your polyatomic ion sulfate. Once you have your 2 possible products, you're going to balance your reaction. Using a coefficient to have the same number of each element on both sides of your reaction. 1 barium, 1 barium, I don't need anything. I have 2 chlorides and I have just 1. So I'm going to put 2 right there. And then that is changing my number of sodiums to 2, and I have 2. 1 sulfate, 1 sulfate, so I think that's it. You don't need anything else. So all of your other coefficients are going to be equal to 1, besides the last one. So you're combining the ions to get your 2 possible products. You're balancing your reaction after checking if you need any subscripts on your formulas. Now you need to identify, out of my 2 products, do I have a solid, do I have a precipitate? So to do that, you're going to use your solubility rules. And you can check your solubility rules, but I made a note here, which is something that if you remember, it will cut down the amount of time that you have to spend trying to find out if something is soluble or not. In your rule number 1, rule number 2 in that paper, in rule number 1, any compound containing an element from group 1, a metal from group 1, You can combine those metals in group 1 with any negative ion and they will always be soluble. And then in rule number 2, you have your nitrates, chlorates, perchlorates, and acetates. All of them are always soluble. You can combine nitrate with any positive ion, acetate with anything that you can think of with a positive charge, ammonium with any negative ion, and all of them will always be soluble in water. So if you use this here, and you already know that you do have a precipitation reaction, I will say that that one right there, it's AQ, because you have a metal from group 1. And whenever you have a metal from group 1, you will have a soluble substance. So barium sulfate is probably insoluble, but you have to check just to make sure. Sulfates here are listed as soluble. It's your rule number 4. It's listed as soluble, but you have exceptions. Yeah? So on your exceptions, you have sulfates combined with calcium, strontium, barium, silver, mercury, or lead. When you have sulfates combined with any of these ones here listed on your exceptions, it means that those are going to be insoluble. So sulfates are soluble, but if you have them combined with any of these positive ions here, they will be insoluble, which means that barium, it's one of your exceptions, and barium combined with sulfate, it's an insoluble compound, and we use the letter S because that will be a solid that you're getting. And that's the precipitate or the product of your reaction. Now I have here two reactions, and you should do the same thing. You're going to combine your ions, ignoring your subscripts, just the ions. After you have your ions combined, now you're going to check the charges to see if you need any subscripts. After you have your formulas with the subscripts that you need, then you're going to balance the reaction and you're going to find out if you have a solid or not. Okay, so we have two reactions here. Make sure that you write down the products, that you balance your reaction, and that you identify the solid of the solid or the precipitate that you're getting out of these reactions. Two more to do the same thing. Write the products, combine your ions, check if you need any subscript, and then after you have your formulas with the correct subscripts, balance the reactions and identify if you're getting any solid. And this is another product. This is asking you if you have sodium carbonate. If you mix this one with all of these four, in which one you're going to get a precipitate. So for this one here, you need to think that you can combine the positive ion with any of the negatives that you have listed here. Positive with negatives. And all of them are going to give you something soluble because it's sodium, and sodium can be combined with any negative ion and you will get something soluble in water. So your other option is looking at the carbonate. Carbonate, the negative ion will combine with the positives here. Okay? And when you have carbonate, right, combined with your positives, now you need to check if you're getting a solid and in which one you're getting a solid. When you combine carbonate with which one of your positive ions here are you going to get a solid. And this is the last problem. Okay? This is a calculation involving stoichiometry and precipitation reactions. So before we do the calculation, you should notice that you're given amount in volume. You have a volume, and that volume corresponds to a solution that has this concentration here. Your solute is lead nitrate. So you have a solution of lead nitrate with a concentration equal to 0.112 molar. And from that solution, you're using 155 milliliters. Without looking at anything else, nothing else in your problem, I'm going to mark down my numbers. A concentration and a volume. Okay? And I'm using the same color for those two because that's volume and concentration for the same solution, a solution of lead nitrate. And then you're trying to find out a volume or a concentration that is 0.2, and that one is for potassium iodide. Now, just to review, molarity is moles over liters. And whenever you have molarity and one more thing, out of the three things that you have in this equation here, if you're given two of them, you can find the third one. You need a volume and you have a concentration of Ki. So you have two things. You have one thing, concentration, and you need the volume. Now for this one here, you have a concentration and a volume. So you have that and this one here, which means that with the information that you have here for the lead nitrate, you can actually calculate moles of lead nitrate because you're given concentration and volume, and you can use those two to find out the moles. So I'm going to rearrange my equation here to find moles. Molarity times liters. The moles that you can calculate with the information that you have, it's moles of PbNO3, which is going to be 112 molar times 0.155 liters. Let me show you why you're doing this. You have a volume and a concentration for lead nitrate. I'm not using this because that's for potassium iodide. You cannot use concentration of potassium iodide with volume of lead nitrate because those are two different solutions. You can use volume and concentration for lead nitrate. Those two, they go together because this volume is from this solution of lead nitrate, and you can use those two to find out the moles of lead nitrate. Now, the problem is asking you to find out a volume. That's what you want. So whatever you're doing here is not going to give you your final answer, but you need that information to get to the final answer. If you want to find out a volume, I'm rearranging your equation in a similar way to what I did for the moles. I'm rearranging this equation to get the volume in liters. This here goes in blue because that's for the KI. If you want to find out the volume, which is what you need, of KI, you need the moles and the concentration. The concentration of KI you have right there, 0.20. But you don't have a number of moles of KI to plug in here to calculate your volume. That's why you need this part here. When you do this calculation here, what you're getting is the moles of lead nitrate. But you have an equation here, a chemical equation that is balanced, that you can use to convert your moles of lead nitrate to moles of potassium iodide, which is what you need right there. That number of moles that you need moles of KI you can get using stoichiometry. So I have 0.112 times 0.155, and that's my volume in liters. I'm not writing 155 milliliters because that's molarity, and molarity it's moles per liter. So I converted my volume right there to liters instead of milliliters. So that number .0174 when you do 0.112 times 0.155, that is giving you 0.0174, and those are the moles of lead nitrate. And you need the moles of KI. Look, what you need is moles of KI. The molarity of KI is 0.020 molar. That's in your problem. So from your stoichiometry, look, every 2 moles of potassium iodide needs 1 mole of lead nitrate. So this is 2. Which is going to be that number times 2. That's moles of KI. Now you have everything that you need to find out the volume that you're trying to calculate in your problem right there. You have the moles of Ki and you have the molarity. So if you divide your number of moles for Ki by the molarity of Ki, that will give you liters for Ki. Mole over molarity, that will give you a number in liters. Let me check, that's 0.174, that's liters, okay? And then if you convert that volume to milliliters, which the problem is not requiring you to do that, it's just asking for a volume, okay? But just in case, that will be 1,000 milliliters in every liter, which means that that will give you 174 milliliters. So whenever you have a problem giving you the chemical equation, it means that you have to use stoichiometry. If you don't use stoichiometry, whenever you're given the reaction, it means that your problem is probably wrong. So, volume, concentration to find moles of lead nitrate. Now, your problem is asking you to find a volume for a solution of potassium iodide. To find volume of potassium iodide, you need moles of potassium iodide and concentration of potassium iodide. So you're using this information to get the moles of lead nitrate, stoichiometry to find the moles of potassium iodide, and then you can calculate your volume. So there's a problem for you to work on. It's the same thing. You're given volume and concentration for copper chloride. You have your reaction, and you're trying to find out a volume for sodium phosphate. And the answer for this one should be something close to, not exactly the same, close to 37 milliliters.